Hello, everyone. Today we're going to talk about phase field models, or PFMs, which are incredibly powerful tools for modeling phase transitions and interface evolution in materials and physical systems. We'll walk through the fundamentals, advantages, and challenges of the method, where it's applied, and a bit of the historical development that led to the models we use today, as well as governing equations for the models and some model examples. So, what exactly is a phase field model? At its core, a phase field model is a mathematical approach used to simulate the dynamics of interfaces, those boundaries between different physical phases like solid and liquid, or two grains in a metal, or even different components of a cell membrane. Now, in a traditional modeling approach, interfaces are often explicitly tracked using sharp boundary conditions or moving mesh techniques. But this becomes incredibly complicated when the interfaces change shape, merge, split, or disappear. Phase field models solve this by using a continuous variable called the order parameter, which smoothly varies from one phase to another. So instead of explicitly defining where the interface is, the model captures it explicitly through gradients in this order parameter. A value of 1 might represent the solid phase, 0 might be liquid, and the transition happens gradually in between. This makes the method extremely robust in handling complex geometries and topological changes, like grain boundary movement or crack branching, without having to manually adjust the mesh or track interfaces. Another key point is that PFMs are typically governed by partial differential equations, like the Allen-Kahn or Kahn-Hilliard equations, which describe how the order parameters evolve over time and space. These equations are derived from variational principles, often minimizing a free energy functional, and they naturally incorporate thermodynamic consistency. Let's dig into the strengths and weaknesses of phase field methods. On the advantage side, the first big one is simplicity in handling complex interface dynamics. Because the model relies on a continuous field, we don't need to explicitly define where the interface is or how it moves. This makes it really effective in situations where interfaces merge, split, or become highly irregular, like during dendritic solidification or crack branching in brittle materials. Second, phase field models integrate extremely well with other physical models. The PDE based framework makes it easy to couple the phase field with thermal fields, stress fields, diffusion equations, and much more. For example, we can model a solidification process that also involves heat transfer and mechanical deformation, all within a single consistent framework. Third, the methods support topological transitions very naturally. For instance, grains growing and coalescing in a metallic alloy. Those transitions are very difficult to track manually, but are easy for a phase field model to simulate. And lastly, it scales well between 2D and 3D. You don't need to change the modeling framework, you just solve the equations over a three-dimensional domain instead of a two-dimensional domain. That's a big advantage when moving from conceptual studies to more realistic simulations. With all that said, PFMs come with challenges. The first major issue is computational. Because the interface is diffuse rather than sharp, we need a high spatial resolution to capture the transition zone accurately. That usually means fine meshes and small time steps, which dramatically increase computational cost. Also, variable selection and model calibration are critical. The choice of free energy functions, mobility parameters, and boundary conditions can strongly affect the results. You need good experimental data or theoretical guidance to tune your model correctly. Another challenge is in modeling sharp features. Since the interface is inherently smeared over several grid points, it's not ideal for problems that require a sharp boundary, like modeling sharp cracks or interfaces in fracture mechanics. And finally, when you start coupling the phase field model with other physical processes, especially if those are governed by stiff equations, you introduce numerical challenges. Solvers must be carefully selected, and simulations can become quite heavy in terms of both memory and compute time. Despite the limitations, phase field modeling has found a huge number of applications. First and most notably is solidification and crystal growth, a classic application for PFMs. Researchers have used PFMs to simulate how crystals grow from a melt, forming dendrites or complex grain structures that are influenced by thermal gradients and solute diffusion. Another major area is phase transformations, like austenite and martensite transformations in steels, which are critical in metallurgy. Researchers have done work on simulating these transitions with phase field models, capturing microstructural evolutions in alloys. Then there's grain growth and recrystallization. These are fundamental in material processing, especially during heat treatment. PFMs can track how grains grow, shrink, and rotate over time. Crack propagation is another fascinating area. Researchers have shown how PFMs can be used to model fracture mechanics, especially in brittle materials. You can simulate not just where a crack starts, but how it grows, branches, or even arrests, all without explicitly defining a crack path. Thermomechanical coupling is another popular application. Researchers have demonstrated models where thermal and mechanical fields interact with the phase field. For example, simulating phase changes in a solid under stress and temperature gradients. And finally, we're even seeing PFMs in biological modeling. Researchers have applied the method to model membranes and vesicles, systems with soft, flexible interfaces where topology plays a key role. This versatility is one of the biggest reasons PFMs are used so widely. You can apply the same underlying modeling framework to systems in metallurgy, geology, biology, and even chemical engineering. The origins of phase field modeling go all the way back to van der Waals in 1893, who introduced the concept of a diffuse interface in the context of fluid mixtures. This was the seed idea for what would become the phase field concept. Then in 1937, Ginsburg and Landau took that idea further. They introduced the notion of an order parameter in their theory of superconductivity, and their free energy functionals form the basis of many modern PFM equations. In the 1950s, Hillard applied the concept to spinodal decomposition using the order parameter as a field variable that could describe microstructural evolution in alloys. Kahn and Hillard followed soon after with their formulation of the conserved order parameter dynamics, capturing phase separation in binary mixtures. Then came Allen and Kahn in 1972, who looked at systems with non-conserved order parameters, such as antiphase domain coarsening. These two governing equations, Kahn-Hillard for conserved systems and Allen-Kahn for non-conserved, are still foundational in modern PFMs. By the 1980s, Fix developed a first-order transition model, and Langer emphasized the importance of phase field approaches in studying complex microstructural phenomena. So while PFMs feel modern because of their numerical and computational complexity, they actually rest on over a century of theoretical physics and material science development.
Now that we've covered the background information and the historical development of phase field modeling, we can now move on to some of the general principles and discuss some of the equations that are generally related to phase field modeling. So first we can look at the Allen-Kahn equation. So this equation is used to show separation of phases for alloys, which contain multiple components. So below we have the original form of the Allen-Kahn equation. And it can be seen that we have our mobility term multiplied by a constant epsilon and our state variable eta. And from that we're subtracting the double well potential. Next, there's the Kahn-Hillard equation. So this is used to represent the separation of phases for binary fluids, and it also describes the concentrations of these fluids. So below we have the original form of the Kahn-Hillard equation. So this equation is describing the diffusion concentrations. So the term that is in parentheses can also be written as mu, and it can be defined as a chemical potential. The concentration terms denoted by C are often defined as a minus or plus 1. So moving back to the Allen-Kahn equation, we can discuss some of the specific characteristics of this equation. So the Allen-Kahn equation is a second-order equation. It is parabolic, meaning it is nonlinear. It is a partial differential equation. And this equation is non-conservative when describing its field order. Below, we can see an example of the Allen-Kahn equation. But the equation was written specifically to describe anti-phase coarsening. So the equation is still describing the phase changes, so it's modeling the phases, but just in a different manner. Some of the more specific applications for the Allen-Kahn equation include dendritic growth, image in painting, and phase separation. Next, the Kahn-Hillard equation. We can look at some of the characteristics that define this particular equation. It is a fourth-order equation, so unlike the Allen-Kahn, which is a second-order equation. Similarly to the Allen-Kahn equation, it's parabolic, meaning it is also nonlinear. It is also a partial differential equation. However, the Kahn-Hillard equation is conservative when describing its field order. Off to the side, we can see the Kahn-Hillard equation, once again written to describe a particular phase separation scenario. The Kahn-Hillard equation can be used for other specific applications, which include phase separation, tumor growth, multi-phase fluids, which are defined to be incompressible, and image in painting. So it can be seen from the two example equations that they both resemble the original forms that were described in the general principles section. The Kahn-Hillard equation and the Allen-Kahn equation are also similar to one another. And it should also be noted that both of these equations have some similar overlap in terms of the topics and areas that they can be applied. Next, we will move on to some hand calculation examples.
All right. Having looked at some fundamental equations, let's now focus on hand calculations. And for this, the example I'm choosing is fracture propagation. We will try to understand fracture propagation, its mechanics, using phase field modeling. So fracture propagation basically is the scenario where a fault, a fracture in some material spontaneously starts progressing. And this can be studied using some simple approaches like traditionally Griffith's approach is very popular, but we can also study this using phase field. And the way we do this is we assign phase field variable to the fracture. So in this image, you see when force is being applied on a material, it experiences some stress. That creates a fracture, a crack. And now what we do is we assign a phase field variable to the material itself, and we assign a phase to the fracture as well. We call material 0 and the fracture itself is called 1. And the transition is the propagation of that fracture. Now to study this thing, we can assume a total energy functional, which is a function of displacement and the phase itself. Now, this total energy functional depends on certain values. It depends on critical energy release rate, and it depends on the surface density function. If we want to solve this energy functional, we need to assume a value for a functional form of the surface density function, which is, as a very common choice, is what is given in equation 2. Now we can also use the equations from Euler-Lagrange's to define the mechanical equilibrium and also phase field evolution. So using these 4 equations, equation 1 to 4, we can solve for crack propagation in a force, in a field, in a material. Now let's look at our specific example, which is a 1D bar which is being pulled apart from 2 of its ends. So this image shows the scenario. There is a bar which is of length L, and when we are applying force outwards, like it's being ripped apart, so that time the bar will displace a little bit, and that displacement is called u of x, and phases will be called phi of x. And boundary conditions are that displacement at the length 0 of the bar is 0. Initially there is no displacement, and as we progress towards along the length of the bar, the displacement is u at a certain point. And also initial condition, because material is not cracked initially, so phi of x initially is supposed to be 0, and it's almost becomes 1 at the end, because the material, we are trying to take material to its failure. We can then use the energy equation that was in previous slide, the equation 1, and define certain parameters. We are going to define here the first derivative of displacement and the first derivative of phase itself. And once we have both the mechanical and phase field evolution equations in hand, we can start to solve our equation. And we can do this in 3 steps, where the first part is to compute strain. So for this, we first divide our material into 3 points. And when we do it, the second point, like one point at initial, like the starting length, the second point is at the end, and the third point is in the middle. And based on these points, we get 3 displacements, and we also get 3 phases. Like these are the points where we will do our calculation or observations. And here are the boundary conditions, as we mentioned before. We can compute strain using equations 8, and by definition, strain is displacement divided by length. So it's the same formula that we are applying to get the equation number 8. And when we put these values in the mechanical equilibrium equation, that is the equation 6, we and with proper boundary conditions, so that stress at the crack is nearly 0. And also we can use the phase evolution equation, that is the equation number 7 in previous slide, to get the expression for GC, that is critical energy release rate. And this gives us the fundamental equations, like we can put the numerical solutions to it and get the answer. So now let's quickly recap what we studied about crack propagation. So crack propagation is when the displacement increases, the strain in the neighboring points of any assumed point in material also increases, and when the local energy release rate exceeds the critical value, that is GC of the material for a specific material, the crack starts to grow spontaneously. And that is what crack propagation essentially is. And how did we physically interpret the phases and the material itself? and that was by assigning phases to material and crack. Material was called phase 0 and crack was called phase 1, whereas the crack itself was the transition between these two phases. Now, Taylor will continue with numerical examples.
Based on the hand calculations provided by Nishant, we are able to use given parameters, including stress, Young's modulus, and energy release rate, to calculate the Griffiths criterion to solve for critical length, okay? And this critical rank is essential for our simulation utilizing Python because it allows for applications related to mineral engineering, to structural engineering, and to many other fields which we will discuss in the following slides. But following our simulation, we're able to calculate a critical crack length of 0.6 millimeters in length under the given stress conditions listed above. And this model is very useful and interesting, as we can see that we've denoted the 0 to be the pore space and the 1 to be the material. So after around 20 seconds of running this simulation, we notice that we're able to develop a crack along the total distance. Interestingly, though, you are not able to distinguish what the critical crack length is actually in the final simulation from Python. We actually have to have this as a separate output that we receive in conjunction with this simulation. And once again, this simulation is very useful with respect to certain fields that experience a lot of stress, like construction, mining engineering, and many other fields that employ stress. And so kind of departing from our simulation that is based on the hand calculations provided above by Nishant, we're going to look at a video of propagating crack. And this video, I just want to point out before we start it, that we have an initial pour at the surface of this simulation. And so we see that this crack is going to propagate across the medium, again under what we assume to be tensile strength relations. And you can find this paper actually located within our references. So we're going to go ahead and play it. Okay, so once again, you'll notice that it does take a brief second at the beginning before the crack becomes spontaneous and just goes through the entire material. And so this is, again, very helpful for a variety of fields and is common practice in a majority of fields. And so we're going to move on to some other example applications in a variety of fields that have been mentioned previously, but in a little greater detail in terms of how they can be applied in multiple industries. All right, so outside of fracture propagation phase field modeling, this kind of modeling has been applied specifically in the field of mineral dissolution through one specific author that I've looked at, known as Li Heng et al. 2023. And this model specifically is interested in addressing changes in pore space within a variety of calcite grains specifically, and interested in the relationship between permeability and porosity. And so to our figure to the right here, this is going to be figure 10. We again see that we've got two cases. We have model A through C, and we've got model A prime through C prime. So these two models initially look very different, with one looking a little more wavy and the other one looking a little more consistent with a vertical plane moving across what appears to be the medium. And so let's go ahead and let's start with what kind of looks like the more fun version here on A through C, and we see that these blue dots essentially represent the calcite grains, right? And so we notice that we have what is referred to as advective flow, and this is kind of the faster flow that you maybe attribute within a river, moving from the side where we have A denoted to the other side. And so really what the big takeaway here is, we see that advection initially starts much stronger at the inlet flow, as we see that over time we have these initial blue calcite grains become smaller and smaller across time until eventually we almost have zero calcite grains. And one more thing to mention about this is that this advective flow occurs much slower than we're going to see in our next example here to the right. So moving on, this very different example here on the right is going to be under conditions of diffusion. And so this diffusion flow is actually much slower than our advection flow. This is not going at the pace of your rivers you might compare this to. And so we see that a lot of our diffusion is happening initially at the beginning of this pore space and then moves further slowly through this area until eventually that we kind of have this asymmetry. We go from having this very vertical line of diffusion to almost this curved area at the upper corner of the outlet. And so this is very different than what we see in the advection phase. And this is very interesting because it kind of corroborates what we tend to see a lot in the experimental material. We tend to see that a lot of experiments tend to see through advective flow that you have this kind of initial faster dissolution that kind of slows down over time. And then with your diffusion, you have a lot of diffusion that happens initially and then also tends to slow over time. However, we find that the Kármán-Kozeny or the Kozeny-Kármán law does not apply in both of these conditions. We find that one, the gradual pore evolution is accurate, and in the other case, we have this asymmetry that happens with the initial advection counting for less than 15% of pore space change, with that being a lot different in the advection because it looks like we still have a lot more pore space available within our B prime versus our initial B. And so this is very interesting and contributes to the overall conclusion established by Li Heng et al. 2023. And so moving forward from here, we're going to look at some other examples.
Hello everyone and welcome to our presentation, and my name is Sheson, and I'll be speaking on some of the applications of phase field modeling. And like my colleague Jack has spoken on mineral dissolution, I will be speaking on pit corrosion and reactive hair brazing. So let's jump in. So as we can see on the firstly I'll talk on pit corrosion, and as we can see on this slide, pit corrosion is a serious form of localized degradation that often occurs undetected until it's late. So on the right hand side we can see an image of real micrograph of a metal which is steel, and after the prolonged exposure to corrosion environment, we have, as you can see, we have some dark spots, which is the corrosion pit, which is a tiny yet and potentially catastrophic cavity where metal has degraded. This pit can compromise structural integrity, and it could lead to failure if it's left unchecked. So how does this process start, and how can we predict it? And as you can guess, we can predict with phase field modeling. So below we can see the simulation where it comes into play, and in figure A we have a microstructure of metal grains and boundaries mapped out, and these grains, this grain boundary occur as a pathway or starting point for corrosion. And as we can see from images B to F, there's a progression of pit growth which is modeled over time, and you can notice in the images that we have some blue regions which represent the corroded materials and how they expand over time. For example, we have from over 73 hours to 300 hours, and these images are gotten from the references we just have down there. And also I would be moving on to the second application, which is reactive hair brazing. So yeah, reactive, we're not just like working on how to prevent corrosion, but we're also like trying to create strong reliable joints between materials, and oftentimes it could be ceramic or metals, using a high temperature process in presence of reactive gases. So as you can see here, we have silver and copper oxide, and which is, yeah, like it's very tricky to mix this to liquid, and when we try to do so, it doesn't like mix uniformly, which creates like a major challenge in the formation of joints. So as you can see in the top image, we can see a simulation frame, and this captures the evolution of the two faces system during browsing process. And from figure A to D, we can see how the face separate and how they spread, forming different boundaries. And this, this segregation affects how the fillers with the the surrounding environment, and how whether the joints hold under stress. And we can see below the second images, these images like they dig deeper into how various parameters affect this process. And in row A, we have, it talks about how the images is just how contact angle, how it varies, how wettability, contact angle is like it tells us how an image sorry and how a material could how easy it could easily get wet. And the image in row 8 talks about how contact angle changes, and illustrates how the wettability can vary with the surface energy. Likewise, in row B, we can see the image. We can see the image which tells us how the change in volume fraction, how they influence or how they determine how much of faces dominate, and how much of a face dominates and how it behaves. And likewise, lastly, in row C, we could see the variation in interfacial energy control, and how easily the faces spread and how they interact with different faces. And likewise, this simulation, they provide us with insights on how we can optimize the brazing process, and choose appropriate materials to prevent defects during a single experiment. So in conclusion, whether we choose mineral dissolution, whether it's the through degradation through corrosion, or construction bound through brazing, we can tell that face field modeling is really really powerful lens which helps us see what happens in micro or nanoscale before the results could show up in the real world. Thank you for listening.